primordial black holes. This is an idea that, in addition to the stellar mass black holes and the supermassive black holes, which we kind of understand how they formed, death of a large star, merging black holes together, you can get black holes of various sizes. But one really interesting and intriguing theory is that there are other black holes out there that weren't formed through natural stellar processes, but were actually formed in the earliest moments of the universe. That you had inflation, then you had primordial black holes, then you had nucleosynthesis and the other early moments in the universe. And so physicists and astronomers have been searching the universe for any kind of evidence that these primordial black holes are out there. And one intriguing possibility is that primordial black holes can explain dark matter, that if you are looking for something that is massive and invisible, a black hole fits the need. But it's really hard to explain how black holes could be all of the explanation for dark matter. And so the problem is that when you have the various explanations for how primordial black holes might have formed, this should lead to various implications for the cosmic microwave background radiation. But those observations haven't held up. And so my guest today is Jason Kristiano. He's a researcher at the University of Tokyo, and he and his colleagues have developed ways that you could get primordial black holes, and yet they could exist in the universe and not be present in the cosmic microwave background radiation in the way that astronomers had currently expected. So it is a very advanced conversation at the very limits of what I understand about the universe and cosmology and physics and so on. And there is a few places, I'm sure, where Jason was saying things and I wasn't fully comprehending them, and so you'll probably notice them. But anyway, this is a very advanced conversation, and so if you kind of get into it and you're like, oh, this is beyond my pay grade, I totally understand. And yet, if you're looking for really nitty-gritty details about inflation, about primordial black holes, about the hope to try to merge quantum mechanics and gravity to come up with a quantum theory of gravity, there's a lot of really interesting insights in this conversation. All right, enjoy this conversation with Jason Kristiano. Jason, I talk a lot about primordial black holes here on the channel as a possible explanation for dark matter and just as an interesting thing for people to look for, but I kind of gloss over that formation process. So take us back to the very beginning of the universe and the chain of events that would go from, say, inflation through to the actual formation of those primordial black holes. What would, step by step, what happened, if they exist?
Yeah, so maybe before I describe the formation of primordial black hole, maybe not all familiar with what is primordial black hole. So primordial black hole, by definition of primordial, is black hole form in the early universe. So we should see it in contrast with standard black hole that we know. So when physicists usually, or general public say black hole, we usually refer to astrophysical black hole or stellar black hole, which is originated from gravitational collapse of a star which is heavy enough to have gravitational force to collapse into black hole. Yeah, that is the standard black hole that we know. However, in case of primordial black hole, this is very special because, we know in the early universe there is still no structure formation. I mean, we can have star because first we have galaxy. So inside the galaxy system, there is star. So formation of star is much after galaxy formation, in the late time of the universe. However, in the early universe, we still have no structure. So it's make it curious whether is it possible to have black hole in the early universe, or maybe the question is there any possible formation mechanism of black hole in the early universe? Yeah. So currently we have we have understanding of cosmology as Big Bang theory. So Big Bang theory is the standard theory of the evolution of the universe. So starting from radiation-dominated universe and matter-dominated universe and to dark energy-dominated universe. However, it's incomplete picture. So before that radiation-dominated universe, before the Big Bang, we have a period called inflation. So here, inflation is that you start from a very, very tiny universe, and then in a very small time, like 0.00032 times, and then it's expand like 26 order of magnitude. So 1000 26 times. So inflation is that expansion of the universe, very rapidly, very rapid, and to become a very huge universe. And then, so we have enough evidence that structure of our universe is formed in this period, in this early inflation time. So we know there is galaxy in our universe, and then it's formed because there is fluctuation in the early universe. So if our universe is completely homogeneous, there will be nothing. So we will be not here today, and there will be no galaxy. But this small fluctuation becomes very important because it is the seed of our structure now. So here is the things. So the standard formation of black hole is like this. So we know that a fluctuation is characterized by a wavelength and amplitude. So wavelength, you can imagine that what is the length of the wave, and the amplitude is the vertical direction. And then, so fluctuation with wavelength, as long as this observable universe is a seed of our structure formation. However, we can have fluctuation with very, very small wavelength that might has large amplitude, and that large amplitude might collapse into primordial black hole. So the idea is still the same is similar as the standard black hole formation. So standard black hole formation is gravitational collapse of a star with a strong gravitational force, or in the general relativity term is strong curvature of space-time. And in this case, so that fluctuation also curve the space-time very strongly, and then if it has large amplitude, it can possibly collapse into black hole. So that is the formation, how primordial black hole can be formed.
And so I want to make sure that I understand this properly. So, when we explain, say, a black hole, a stellar mass black hole, and how you've got, a star that's more massive than the sun, it's going through fusion in its core, runs out of, reaches iron, it's no longer able to fuse, and then it implodes. All this material falls in and compresses all of this matter into a very small area, and the escape velocity exceeds the speed of light, and you end up with a stellar mass black hole. But what you're describing, you're thinking of it from a space-time perspective, that you're seeing space-time sort of, the amplitude and the wavelength of the space-time itself that is so small that a black hole is the result, and that you can, early on in the universe, end up with those same kinds of conditions just purely because that's what was happening in the universe shortly after inflation. And so these black holes are just forming naturally out of the universe itself. Is that right?
Yes. So that is the scenario. Of course, we have to find observational evidence of that large amplitude. So we still have no observational evidence of that possible large amplitude of short scale fluctuation in the early universe.
But when we say fluctuation, we're talking about fluctuations in space-time itself.
Yes. So you can imagine that so some kind like this. So in general relativity, we know that gravity as a curvature of space-time. So fluctuation of space-time can be imagined as, so a region here has a very strong curvature and another region has a weak curvature. That's how to imagine fluctuation of space-time.
Right. And so if any of those regions reach some amount, if the fluctuation is overly dense in one area, if it crosses some line, then you have the conditions for these primordial black holes.
Exactly. Sure.
Right.
Exactly. Yeah.
Yeah. Okay. So we've got that period of inflation, and like what kind of a time frame? If we, there's always that famous idea of like the first 6 minutes, after the Big Bang. What kind of time frame are we looking at for when the conditions are right for these primordial black holes to form?
Oh, if we talk at inflation time scale, it's like Planck time. So 0.0032 times 10 to the power of minus 32 second in the very beginning of the universe. So that's the time when that fluctuation formed.
Oh, so they're forming before the the weak force and the strong force are detaching, the electromagnetic force and the first atoms are forming. Like first come the black holes.
So the seed of the black hole, and then in the radiation dominated universe, and that's what you say. So when light, when the universe is full of light, then it can collapse into black hole. But the seed was formed during that in the very very early of the universe during inflation period.
Right. So with a universe that these primordial black holes existed early on and were part of the environment moving forward, what impact would they have on the later stages? The sort of nucleosynthesis region and the cosmic microwave background, area time. How would these black holes be playing a role throughout that evolution of the universe?
Yeah, I think it can affect nucleosynthesis. So there are some way to constrain the theory of primordial black hole that makes this black hole does not disturb the does not spoil this standard theory of Big Bang nucleosynthesis. So yeah, it can have an effect on that Big Bang nucleosynthesis. But recently there is an interesting aspect of this primordial black hole to the formation of first galaxy. So from JWST observation, there is a hint of that the first galaxy is formed early enough. So it's earlier than the previously thought. So there is a hint from JWST telescope. And then one of the postulates is that if there is small amount of primordial black hole, it can lead to earlier for galaxy formation. Yeah, that's one of the effect of the one of the consequence of primordial black hole to the structure formation. And then of course there are a lot of other other observational hint of primordial black hole. For example, until now there are a lot of effort to detect a particle nature of dark matter. So we have convincing evidence that 20% of energy density of our universe consists of dark matter. However, we still don't know what is the nature of dark matter. And of course, the standard theory of dark matter is that dark matter is a particle. However, until now, there are a lot of effort to detect particle dark matter, but still fail. So people try to find some kind of alternative. So how if it's not particle? How if it's actually a black hole? And yeah, of course, if we talk only about a stellar black hole, then stellar black hole is very limited mass. I mean, around solar mass because star cannot be too heavy. However, if we want to talk as primordial black hole as dark matter, we need to have loose range of mass, and yeah, that's exactly where primordial black hole become important. And then another thing is from gravitational wave observation, either from LIGO Virgo Kagra collaboration, and also stochastic gravitational wave background that recently is observed by pulsar timing array collaboration. So there are a lot of observational hints of these primordial black holes recently.
And so, it's been really fascinating seeing the results coming from Webb, like these very massive galaxies seen very early on in the universe, seeing quasars at 700 million years after the Big Bang, and how can you get a black hole with 1 billion times the mass of the sun that has already formed at within the first few 100 million years after the Big Bang. And it would be easily explained, I guess, if they just formed during inflation and they were just there, present in the universe as these seeds. So, based on all these kinds of observations coming from James Webb, is that appearing to be more likely? Is this evidence for primordial black holes as the seeds of these supermassive black holes?
I think, JWST we are still waiting for more data, right? I mean, it's currently still running, and maybe the community is still think this as a good hypothesis, but still not strong enough. Yeah, I think that's about the JWST.
So let's talk about the methods for observing black holes, and we already talked about a bunch of kind of indirect methods of detecting them in terms of seeing early black holes and so on. But what are some proposals on ways that we could actually detect these primordial black holes in other ways, gravitational waves, seeing them evaporate, things like that?
Right. So, interferometer, gravitational wave interferometer, we have in the world currently LIGO, Virgo, and Kagra. So LIGO in the US, Virgo in Italy, and Kagra here in Japan. And it's in the O4 running, so in the fourth stage of running. And then, it's expected to observe a lot of black hole. And then, so previously, in the O3 running, that collaboration already observed many black holes around, so from 1 solar mass until maybe almost 100 solar mass. And then, of course, black hole with around 1 solar mass is easily explained by stellar mass black hole. However, black hole with more than 10 solar mass is hard enough to explain by stellar black hole. So, I mean, you need a lot of some kind of like merger to form a heavy black hole.
To get like 10 times the mass of the sun.
Yeah. If you 10 times solar mass, 10 times mass of sun. If you want to explain that by standard theory, so some people come up with idea how if that heavy black hole is primordial black hole. Yeah, it's fine. You can explain that with primordial black hole. However, it's not the smoking gun of primordial black hole. So here is the smoking gun. If we find light black hole, lighter than solar mass, then it will be the smoking gun of primordial black hole. So, currently we are LIGO Virgo Kagra collaboration is expected to observe many black holes, and we hope that they might observe sub-solar mass black hole, so black hole lighter than mass of sun.
So is there a minimum mass that you're looking for? If you see it, you go, okay, that's it. It can't be formed by a stellar implosion. It has to be a primordial black hole.
Yes, I think that is limited by standard black hole. So the threshold for formation of black hole from star is limited by Tolman-Oppenheimer-Volkoff limit, TOV. The famous Oppenheimer. I think it's around 2 solar mass, maybe.
Okay.
So
if we see a black hole with half the mass of the sun, that's
surely
unusual.
It's very unusual. Yeah.
Right,
yes.
Right. And yet that sounds like it's definitely within the limits of LIGO Virgo. I mean, we think about the Kilonova event. We had stars with, neutron stars with a little bit more than the mass of the sun colliding with one another. So it feels like those, it should be able to detect white dwarf collisions at this point. So it feels like these are in that zone.
Yeah, I think so. So I think that is one of their goals.
Okay.
To find.
But I know there are a bunch of other ways that we might be able to detect these primordial black holes.
I would like to say that it's a way to constrain the theory of primordial black hole. So, like black hole evaporate by Hawking radiation, and then, we can observe gamma ray in our universe, the intensity of gamma ray, and then it can, that intensity can constrain how abundance of light black hole in the early universe that is already evaporate. So I would like to say that is the way to constrain, but still we do not. It's not the. It's still it's not a direct evidence of primordial black holes.
Right. So the fact that we aren't seeing bursts of gamma radiation all around us coming from not stars or not, I don't know, gamma ray bursts. Like there'd be a certain kind of signature that we would see in our gamma ray detectors, and we're not seeing that. And so that constrains the possible masses of those primordial black holes.
Yes.
Yeah. Right. And so, I mean, with those constraints, then, what are we left with? If you wanted to like fully explain dark matter with a certain recipe of primordial black holes that fit within those constraints, what are you left with? What's possible?
Yeah, I think we're still left with a parameter space. So there is so how much do you want to explain dark matter with primordial black hole? So typically when we say primordial black hole as dark matter, it assumes that we explain the total energy density of dark matter, the 25% of the energy density of in our universe, equal to the abundance of primordial, the number density of primordial black hole times mass spectrum. So yeah, if we strict on that, the parameter space is already limited. So we don't have much room. But if we want to explain partially, so some percentage of dark matter as primordial black hole, then we still have a lot of room, a lot of parameter space.
I see. I mean, when I talk to people who are researching dark matter, this is the answer that seems to be coming up a lot more, which is dark matter is probably a collection of things. A little bit of primordial black holes. Maybe we have new theories of physics for gravity that we need to fully understand. Some kind of massive particle. Maybe there's rogue planets. And you add it all up and you get dark matter.
Yeah, and it seems that so there are a lot of observation that so this observation is very well explained by dark matter, and another observation is very well explained by modified gravity on large scale. I would like to say modified gravity because modified Newtonian dynamics, MON already constrained very tight, but modified gravity on large scale might maybe still possible. So it can be the possibility. So dark matter consists of many components, and it can be that primordial black hole only part of dark matter. Part of dark matters. Yes.
Okay. So now I think we've sort of laid out the playing field here. We kind of understand all the bits and pieces here. So let's talk specifically about your research. So you recently published a paper, Physical Review Letters. What were you proposing?
Yeah, so back to that quantum fluctuation in the early universe. So first, we are convinced that we have enough evidence, or currently the leading theory to explain the early universe is that fluctuation behave as quantum. So imagine a homogeneous universe, but quantum always limit our precision. So we cannot be extremely precise homogeneous. So there is always some small fluctuation. Quantum theory characterized
like Heisenberg, like uncertainty, like
Heisenberg uncertainty principle, right? So you have, you always have uncertainty in that homogeneity, and so that uncertainty in the space-time, in the curvature of space-time, yes, it's called quantum fluctuation. And then, so fluctuation with wavelength, as long as the size of our universe, is well understood and well observed in the cosmic microwave background. So that amplitude is tightly constrained by Planck satellite observation. So we do not have, we cannot make any theory. So it's tightly constrained on that scale. So we have to make a theory that fix that observation on large scale. So for fluctuation with wavelength, as as long as the size of our universe. However, fluctuation with shorter wavelength, much shorter than the size of our universe, is loosely constrained. So there are almost no constraint on that. And then, as I mentioned before, if it's large enough, it can collapse into primordial black hole. But here's the thing. So that fluctuation is observed. So back to that large-scale fluctuation. So that large-scale fluctuation is observed in our cosmic microwave background as a correlation function, 2-point correlation function. So imagine like this. So our cosmic microwave background has temperature, background temperature to 2.7 Kelvin, maybe 2.71 Kelvin, more precise. However, there are small fluctuation in each point, like 10 to the power of minus 5 times the background, so 0.00001 times the 2.71. There is a small fluctuation that is distributed normally. So, of course, if you take average, you will get 0. But the distribution is normally. So, some regions are colder, 10 to the power of minus 5 times background. Some regions are hotter, 10 to the power of minus 5 times the background. So it's an extremely precise observation by Planck satellite. Then that fluctuation is observed as is exactly the origin of that temperature fluctuation. So that the long wavelength quantum fluctuation is an explanation for that temperature fluctuation. And we can also observe that 2-point correlation. So if we take 2 points in our CMB, and then we take average, then we find a non-zero value. So that is the one of the convincing evidence of inflation. Yeah, although we still need more observation to rigorously prove inflation. However,
right. Sorry, I just want to stop on that for 1 second. Like, I understand like the Planck observations of the cosmic microwave background and the temperature differences, and how those map to the large scale structure, how those evolve into the large scale structure of the universe that we see today. The places that were higher temperature matched to over densities, places that are lower temperature matched to under densities, and that's where we see in the later evolution of the universe, we see the giant scale structures or the voids. But I don't understand how you're able to connect inflation as evidence into those fluctuations in the cosmic microwave background.
So that fluctuation is stretched by inflation, so it can be as big as our size of our universe. So that fluctuation is created in the very early universe when the size of our universe is still very small, and then as inflation expand our universe, then that fluctuation also
right. Okay. Yep. I understand.
Become the origin of large-scale structure. So here's the point. So I want to emphasize the correlation function. So they are correlated because they are created inside the horizon of our universe in the very early time. And then the key is that, so we observe the correlation of long wavelength fluctuation. And then this short scale, within the same theory, this short scale fluctuation is were also correlated at the early time. So correlated means that they know each other. So our theory is like this. Although there are no observational constraints on the amplitude of the short scale fluctuation, however, we claim that we cannot make any theory with arbitrarily large amplitude, even for short scale fluctuation, because if it's large enough, it can make coherent effect to amplify the amplitude of large long wavelength fluctuation that we observe in the CMB. The key here is that the small scale fluctuation are also correlated from the from the beginning of inflation, and because they know they know each other, they can coherently enhance the large scale fluctuation. So imagine like this. So you have many ant, the small animal, and then that many ants wants to push an elephant. It's almost impossible, right? I mean, if this ants uh, only randomly push the elephant, they cannot, they will never push if they just randomly push. However, if they are correlated in the sense that previously they talk each other. So, for example, please push to that direction. Then, yeah, with many elephants, with many ants, yeah, if they are much enough, then they can push the elephants. Yeah,
Right. And so you're saying that these small fluctuations in the very early universe will then have a sort of follow-on effect to create some of the larger fluctuations that we see in the cosmic microwave background radiation.
Exactly.
Yeah.
So
Okay.
because they are correlated, they can coherently push the amplitude of large scale large scale fluctuations.
And so then what are the implications for what that means as primordial black holes as an explanation for dark matter?
Yeah, so primordial black hole to explain primordial black hole as dark matter, we need significant abundance of primordial black hole, and that significant abundance, we can have that significant abundance if the amplitude of short scale fluctuation is large enough. So the probability that short scale fluctuation to collapse will become large enough, so we have more abundance of primordial black hole. So abundance of primordial black hole is very sensitive to the amplitude of the short scale fluctuations. And if we can prove that the amplitude of short scale fluctuation cannot be large enough, then it implies the abundance of primordial black holes are not significant.
So it's going to take its place in the larger, I guess, group of like, if it is there, it's not all dark matter.
Yes,
it's some portion of dark matter.
Yes, but unfortunately, so the relation is sensitive enough, so it's like exponential, negative exponential dependence. So if the amplitude of curvature perturbation decrease for how to say, it's very sensitive to the amplitude of the curvature perturbation. Yeah.
Right. And so I guess what observationally would you look for to know if you're on the right track?
So we are investigating whether this mechanism to produce primordial black hole is consistent with large-scale structure observation. So if one day we observe primordial black hole, maybe from gravitational wave observation or JWST or any observation, then it means that we require more complicated primordial black hole formation model, which does not rely on the simplest model of the cosmic inflation. Yeah. So we are more testing the consistency of the theory. That's
Right. I mean, like right now, there is no confirmed measurement of a primordial black hole. There is only constraints on primordial black holes. They can't be this big. They can't be that many. They can't be in these places. But the possibility is out there. And yet, if we get that 0.5 mass black hole merging, although it'd be hard to know if it was a black hole and not something else like a white dwarf or a whatever. But anyway, if we do get that, say someone has absolute proof that you have this primordial black hole, then you have to say, okay, well, if these things are forming, why aren't they everywhere? And you're saying, okay, here's why they're not everywhere.
So I would like to say that, so if one day we detect primordial black hole, most likely it's not coming from cosmic inflation. Yeah, although we have to verify what is the abundance of that primordial black hole. So my work is like more verifying what can be the possibility of the formation mechanism. Yeah, if one day we detect primordial black hole.
Yeah. There's so much unknown about the early universe, about, with the cosmic microwave background, that's as far as we can see. We can't see beyond that in the electromagnetic spectrum, but other things, neutrinos, gravitational waves, these things were present and are passed through this cosmic microwave background radiation. When you think about that earliest time, what are the kinds of observations, even in those scales, neutrinos, gravitational waves, would give you sort of a sense of what direction to look for next? What would you hope to, and any kind of observation, if the Big Bang Observatory, gravitational wave observatory comes out and is giving you precise detections of gravitational waves prior to the cosmic microwave background, what would you want to see to then sort of figure out where to go next?
Yeah, so I think we have to differentiate two different gravitational wave observations. So the current ground-based detector by LIGO Virgo Kagra is observing gravitational wave from a specific direction. So it's like if there is a black hole merger in this direction, then this detector on Earth can observe that merger. However, there are another type of gravitational wave detector which can detect a background of gravitational wave. So if gravitational wave coming from all direction in the sky, as a background in our universe, how to detect them? Yeah, currently there is already pulsar timing array collaboration. Maybe in the US it's called nanograph. In the Europe it's called European PTA. And yeah, currently it observes like three sigma statistical significance of the existence of stochastic gravitational background, and it's some kind of like hint also of the primordial black hole, because primordial black hole formation is associated with as I mentioned before, it's coming from large amplitude of short scale fluctuation, and because it has large amplitude of scalar fluctuation, it's also a source of gravitational wave background. So I would like to say that this gravitational wave background can give a hint of the formation mechanism of primordial black hole, which characterized by the spectrum of the gravitational wave. And then so this pulsar timing array collaboration is, I think, already finished, like 15 years. This observation of pulsar timing array. And then
and I think the European one just released their second data release, and just more evidence for but in that case, it's the background gravitational waves coming from, say, merging black holes, not the background radiation coming from primordial, I guess, coming from the early universe, right? It's sort of like two separate kinds of gravitational wave backgrounds.
So it's sure. So the first explanation that you say is the standard theory. However, I think there is a criticism that the standard supermassive black hole merger require to explain that to explain pulsar timing array observation with merger of supermassive black hole need a quite unrealistic merger rate, if I'm not mistaken. So
really interesting. Okay.
Yeah. So some people try. I think in case of the US, the nanograph, they released a paper about hint for a new physics from pulsar timing array collaboration. So some people think about how whether we can fit the spectrum better with new physics, and then so gravitational wave background from primordial black hole can give a better fit, in the sense that better Bayesian statistical factor compared to the standard supermassive black hole merger. However, the caveat is that these new physics are very model dependent, so we have to be careful of
of course. Right.
Yeah, but again, I would like to say that it's a hint of primordial black hole, and then so future square kilometer array (SKA), yeah, will confirm this. So we'll confirm this PTA collaboration observation more precise with better statistical significance.
The square kilometer array, which is a
Yeah.
radio telescope,
Yes.
is going to be able to confirm the gravitational wave observatories. How? Oh, I guess with the precision of the radio measurements for the pulsar timing. Okay, I see. Yeah. So then if it turns out that the mergers between, or even just say supermassive black holes that are in orbit around one another, there can't explain the background gravitational wave, then all that you're left with is the ones that are left over from the beginning of the universe.
Yes.
Is that what you're saying?
Yes.
And if so, then we need new physics to explain how we can have that scale of gravitational waves moving through the universe.
Yes.
I see. Yeah. It's so tough because you've got, I don't know, it's kind of like being in a place, like say you're in a concert and you're trying to listen to a band play with these giant speakers, but you're also got some headphones in and you're trying to listen to some different music, and the two are coming at you simultaneously, and your brain is trying to say, this is the music that's coming from the big speakers and this is the music that's coming from my headphones, and it's really hard to take them apart and go, this is coming from all these giant black holes that are emerging, and that's coming from oscillations in the early universe at the very beginning of time.
Yeah.
I mean, would the wavelengths be different? And would redshift have an effect? I mean, would those early oscillations be also redshifted in a way that's detectable?
So I think that's so the wave that short wavelength can have some range of wavelength. So there are spectrum of wavelength also, and each so and each observation has their own sensitivity to the wavelength. So to the wavelength, and we can convert to frequency. So for example, like nanograph, also, of course by the definition of nano, it's sensitive to nanohertz gravitational wave. And then there are also another proposal of LISA mission. So the satellite to detect gravitational wave, background gravitational wave, but with different frequency range. So there are a lot of observational mission with different frequency sensitivity.
But I guess, like, think about James Webb. When James Webb is looking, it's seeing objects that were once in the visible spectrum, maybe even in ultraviolet, and they've been redshifted into the near infrared. And you could put a infrared or a red star beside one of those galaxies, and you're going to see the same frequency of light coming from those two objects. It's just that you know that one is really far away and one is really close, and one is being redshifted. And so I wonder, when you're detecting the redshift of the gravitational waves, can you know how far away these gravitational waves have traveled to get to you, and how much they've been redshifted? Yeah, I mean, I guess like with, say, merging black holes, how they have to be orbiting around one another, and so what the frequency of the waves must have been at the origin, and then you detect their current wavelengths, and that tells you, how far away they are, and so on. So, but I don't know. It feels like with gravitational wave astronomy, we're in such an early stage, and yet it's such a valuable tool because it's a completely different way of looking at the universe in a way that we've just never had before. And so each one of these missions that comes out, each one of these observatories, will just really help us fill in missing pieces of the universe. It's a way to see through stuff.
Yes.
Well, Jason, what are you obsessed with right now?
Yeah, as my research topic, so I'm very interested to understand the early universe, and I'm looking forward to see the evidence of this cosmic inflation, and I want to know the mechanism of this inflation, which means that the mechanism to produce our observable universe. And
and that would have been a whole separate conversation.
I'm looking forward to this gravitational to see the result of this many gravitational wave observation. Yeah, such as the currently running LIGO Virgo Kagra observation.
But there are several, I guess, indirect observations that give evidence to inflation. Is there something that you would feel that you would love to see to go, okay, inflation, like we don't know if inflation happened. Inflation fits the problems with the Big Bang in terms of the homogeneity and lack of magnetic monopoles, et cetera. But is there and there is indirect evidence that this is the case, but is there something that if you saw it, you'd be like, okay, inflation actually happened in our universe?
So I would like to say that the correlation observed in this cosmic microwave background is a very strong hint to inflation mechanism, because it can be correlated only when these two fluctuations are originated inside the cosmic horizon in the beginning of inflation, and then it's stretched by inflation, and then they are correlated. So we already have a strong hint of cosmic inflation. However, the smoking gun of inflation is that when we observe gravitational wave as long as the size of our universe. So the stochastic gravitational wave background from inflation. That will be the smoking gun of.
Wait a minute. So we need to see a gravitational wave with a wavelength that is the size of the observable universe?
Yes.
That sounds hard.
Yes. And so I mean, there is some detecting it is very hard, because the amplitude of that gravitational wave is very small, so it's hard to directly detect that stochastic gravitational wave. But it can leave a trace on the cosmic microwave background as called as a type of polarization called B-mode polarization.
Yes.
Yeah. So.
And I remember like the Bicep 2 experiment hoped to find it, and then it was sort of ruled out as dust again.
Exactly.
Right.
Exactly.
Yeah. So is there an experiment that you think could take a crack at finding the polarization, the B-mode polarization of that primordial gravitational wave?
Yeah, I think recently there is a proposal on CMBS4, maybe if I'm not mistaken, the name. That is, unfortunately, it's not continue. It cannot get next support from the government. Maybe, So there are some proposed observational mission to detect that B mode more precise. But maybe need much more money.
Right. But and so that would be it. Like if you saw, and it wasn't just dust, but you actually saw the polarization in the cosmic microwave background that matched that gravitational waves the size of the universe, then you would go, okay, inflation actually happened in our universe.
Yes.
Yeah. That would be kind of amazing. And I got the impression there was something else you were obsessed with.
Well, as a theoretical physicist, of course, the all obsession of this high energy theories is to understand the unification of all fundamental force. And in order to understand that, we need to understand the quantum nature of gravity. And then, I'm interested to see whether this quantum gravity can leave trace in this large scale structure or CMB observation, or
you mean the thing that Einstein tried to figure out and couldn't?
Sure, that's
yeah. Right. I mean, again, is there an observation that you could make that would give you a sense of the quantum nature of gravity?
Well, so if we look at currently the highest observable energy that we can observe is cosmic inflation. So current bound of the energy scale of cosmic inflation is like 10 to the power of minus 5. So 5 order below Planck scale. So Planck scale is the energy scale where we expect full theory of quantum gravity. And then if we believe like string theory as the quantum gravity, so it means that we say that string scale is some order below that Planck scale, so it can reach called UV completion on that Planck scale, or like good behaving theory with no divergence on that Planck scale. So my interest is that to find the possible signature of quantum gravity theory. That let's say the currently well understood quantum gravity theory is string theory in the statistic of the CMB. So currently people only focus mostly on this 2-point statistic that is already observed in the CMB. However, there are a lot of statistics that we can observe. For example, 3-point correlation and 4-point correlation, which might be observed also in the future large-scale structure observation. So, I'm looking forward to connect this extremely high energy scale, which is the dream of all theoretical physicists, to find the unified theory of this fundamental force, to find the trace of this in cosmology, the signature of this in cosmology.
That sounds like that could be your entire career. And you might end up like Einstein, not finding it. But that sounds like a life well lived. Jason, it was a pleasure to talk to you. Thank you so much for filling in these pieces. Good luck with your research, and good luck unifying physics.
Yes, thank you very much.
All right. I hope you enjoyed that conversation with Jason Kristiano. I'm going to give you my thoughts in a second, but first, I'd like to thank our patrons. A special thanks to Abe Kingston, Andrew Gross, David Giltonen, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Modzo, Paul Rohrbach, Stephen Krasaki, Stephen Fowler Munley, and Vlad Chiplin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. It's interesting when I actually get a chance to talk to the researchers who are working on trying to understand and solve some of these big unsolved problems in physics. Each one of these is just like a monumental task. What is the nature of dark matter? What is the nature of dark energy? Are there primordial black holes? Did inflation actually happen? How could you go from an inflationary universe to the more modern universe that we see today? And there are just like all of these implications, and yet the kinds of theories that have been proposed to try to come up with answers are really tricky observations. And so this is driving a whole new generation of new telescopes, new observatories, new techniques, and even just like new ideas on how to take the data that you already have to try and seek an answer. And the thing that I love the most is to see this constant improvement by both the theorists and the experimenters to kind of push each other forward to say, like, how could we detect the presence of supermassive black holes merging across the universe? I know, let's observe pulsars carefully to detect the ripples of space-time as they're moving past these pulsars. Suddenly a whole new way to be able to do this. And I'm constantly amazed and impressed when I have these conversations and I hear the clever ideas, because I think, a lot of people, they're very dismissive about what the physicists and what the experimenters are doing. But when you actually talk to them and you have a respect for the creativity and the open-mindedness that they have to find answers, to listen to nature, it's really inspiring. And I find it so exciting to sort of think of what's a really clever idea to solve this problem. And I hope, you do as well. All right. We'll see you next time.